if you need the area of a region between two curves, formula is very similar, and with your past experience with area between curves, this is going to make a lot of sense. It's simply going to be 1/2 outer function squared minus inner function squared. So to look at an example, we want to find the area trapped inside the curve 4 cosine 2 theta and outside the curve r equal 2. Now what I would do first with something like this is I would graph those two equations and get an idea of what space we're talking about. Alright, so I've entered my two functions. I've switched the style of the graph to the ball and chain just to slow it down a little bit, and I'm using a a decimal viewing window, which doesn't quite show us the very tips of a couple of those petals, but I can adjust that pretty easily. In fact, let me go ahead and stop that now. I need my y min and max to be just a little bit larger. So let's try that. Okay, that's better. My viewing window is a little distorted, so I'm not happy with that yet. So I'm going to go back and zoom square, which is just automatically going to reset whatever needs to happen to make the picture have the right proportion. Okay. So the area of the region inside the flower petals and outside the circle. So we're talking about this space, that space, and that space. Alright, so really the real work here is to determine what are the limits on this definite integral. What do they need to be? And I need to know when are these two curves going to intersect. That intersection point, that intersection point, that intersection, that end, that one, that one, that one, and that one. So we've got 8 different intersection points. So basically you've got to solve the equation 4 cosine of 2 theta equals 2. When do these two curves equal each other? When are the r values the same? At what values of theta are the r's exactly the same? So you're looking at cosine of 2 theta equal 1/2. So 2 theta, thinking about the unit circle, would be pi over 3. 5 pi over 3. And so on. Okay, this is going to get us started. So theta, the first value of theta in the interval between, starting at 0 and going to something. Actually, I've graphed from 0 to 2 pi, and that gave us the right viewing window. Alright, so it would be theta is pi over 6, 5 pi over 6, etc. So our first intersection point, I don't really know where that is, but I know it's going to occur when theta is pi over 6. So here's what I would do. Change the mode of your calculator to graph these two functions simultaneously. You're set to graph sequentially, which is one at a time. What I'd like to see is the two graphs generated at the same time, so I can pinpoint which of these intersection points is the quote-unquote first one. There. Okay, so theta equals pi over 6 corresponds to that point on our curve. Now the two curves started on the x-axis. So if we looked at the interval from 0 to pi over 6, that would give us the area of this little space right there. One way to do this problem is to integrate from 0 to pi over 6 and then recognize that that is 1/8 of the total area we're trying to find. Multiply your area by 8. So that's certainly an option. What I would like to do, the way I would like to think about this is that I've got 4 petals, and if I can find the area of one of these petals, so if I can find the area of that entire space using a single integral, then multiply that by 4, and that just makes sense to me. So what I think is, if I started at negative pi over 6 and stopped at positive pi over 6, I think that I would just be looking at this section of the area. So I'm going to change my viewing window to check that out. Oops, I don't need 3 of those, or 4 of them. Alright, pi over 6 over 6, there we go, and positive pi over 6. Yes. So the way I want to set this up is I'm going to multiply by 4, integral from negative pi over 6 to positive pi over 6 of 1/2 times, our outer function is 4 cosine 2 theta, and that's all squared, minus 2 squared d theta. You could also set up the integral 8 times 0 to pi over 6, 1/2 4 cosine 2 theta squared minus 2 squared d theta. Either way you go with that, you should get a total area of 15.30578. Again, use your calculator to evaluate those integrals. They are things that we could do by hand, but there's just really not any reason at this point for us to do that work.